Okay. Cool. So before we begin, I just wanted to clarify something. The last class, when we were discussing about the effect of zeros and the causality associated with it, I made some loose statement. I just want to correct it. So I made the statement, right, that the zero will be always greater than the pole location. So it turns out it need not be the case all the time. So if the circuit only has grounded capacitors, you can say that. But it turns out if you have floating capacitors, it's not this. I mean, example circuit is this. So let's say you have something like this. Say this is the input and this is the output. You can work out yourself and find what are the zero and pole locations. Here you will find that the pole is at a higher frequency than the zero. Okay, the bottom line is the causality, as I explained, comes from the fact that if you apply any input to the system, the zero basically pushes the output at t equal to 0 plus in the correct direction. It's not as though the output starts to respond for t less than 0. Okay, that's all. So with that, let's continue from where we left off. So we are looking at the idea of frequency compensation, and basically we came up with two techniques. One was to make sure that the open loop poles are far apart, and the second was to introduce an LHP0, right? And we saw that in both the techniques, what we are essentially doing is trying to make the system behave like a first order. Yeah, it's stable, but we wanted to make the system behave like a first order system around the unity gain frequency. So that's what happened in both the techniques, right? And as you guys pointed out, the first technique where we were keeping the poles far apart was very similar to the effect of pole splitting we discussed in the context of a common source amplifier. So first let's refresh that result first, and then we can use that. So this was the common source amplifier. We had input, we had a source resistance Rs, an input capacitance C1, and the transistor I modeled as a GM block, and at the output we had R2 and C2, and we also had a capacitor around the GM like this. So now when we didn't have this capacitor C around the GM, what were the pole locations? Minus GS by C1, right? And the second pole at the output was at minus G2 by C2. And we remarked that these two could be actually close by, right? And the moment we added the capacitor, what happened to the first pole? What is the conduct? I mean, the moment you add the capacitor, again you are introducing coupling between these two nodes, but we made an assumption that one of the poles is much farther apart than the other, that you could treat them as though they were uncoupled poles. So we tried to look at the effective conductance at that node, and what was that? What is the conductance in this node? Total conductance? It was just minus GS. And what is the total capacitance? We have C1, and then this capacitor, it gets multiplied by the gain. So that was C1 plus C into 1 plus GM by G2. I'll write like this, right? Now similarly, if I look at the second pole, so first, what is the total capacitance at the output node now? So I have C2, and then what happens? These two guys, series combination of these two guys in parallel with C2. That was the total cap roughly. So the denominator is this C2 plus C1C by C1 plus C. So what is the conductance? We have G2, so that should come directly. And then, oops, hold on, let me write it clearly. This is G2. And we also saw that if you apply a test voltage here, we have this capacitive division happening. So a fraction of test voltage appears at this gate or at the input of the GM. So which means the GM will draw some real current proportional to the fraction of V test. So what is the conductance then? I mean, if we apply a test voltage here, what is the fraction of voltage that appears here? C by C plus C1 times V test. So what is the current it draws? GM times that voltage, that's all, right? So what is the conductance we have? Same, right? I mean, I apply a test voltage Vt, I see that we seem to be drawing this much amount of current. So the conductance is what? So, oops, okay, Gm C by C plus C1. And basically this one was moving to a low frequency and this moved to a high frequency. So now let's look at our two-stage OTA. So let's say this is the first stage having a transconductance capital Gm1. At this node, say the total conductance is G1, the total cap to C1, and then we'll have the second stage. Say it has a total transconductance Gm2, the conductance is G2 and capacitance is C2 at the output. Right? So in this two-stage OTA, again, normally what is the first pole location here? Same, right? I mean, these two are actually uncoupled. I can directly say what is that? Minus G1 by C1. Second pole is at G2 by C2. Again, these two might be close by, and that's why we want to basically separate them out. Now, if you think about it, this circuit here is very similar to what we have here. Okay, see here I have a voltage source in series with a resistance Rs. I can change it into voltage source in series with a resistance. I can change it to a current source in parallel with a resistance, right? So if I were to do that, I'll basically have a current source, say V in times GS and Rs, right? And in the two-stage OTA, this is basically a current source, right?
Yes, sir.
So basically they are the same. So now here I see that again the two poles are close by. I want to separate them. So what can we do now?
The
Capacitor across
GM2 block.
GM2, right? Here we had the same thing, right? When we didn't have the capacitor, these two poles were close by. The moment we put this capacitor, they split up. So we'll do the same thing. So I'll go ahead and put a capacitor around GM2, right? Oops, give me a moment. Okay. So this capacitor I'll call CC, stands for compensation capacitor. Okay, so the moment I add the capacitor, what will happen to the first pole? Again, it's approximate. What is the first pole location approximately? the conductance is G1, and then total capacitance is
C1 plus
Cc into 1 plus Gm2 by G2. Okay. So this is the first pole. What about the second pole?
minus C2.
Yeah, first let's write the capacitance. So capacitance we have C2 and these two guys in series. So same thing. C1 Cc by C1 plus Cc. And if I write to conductance, I'll have G2 plus the capacitive division between these two caps. Okay. Now, of course, this we can in turn approximate, like in the denominator for the first pole, which of the terms do you think will be dominant?
Second.
This guy will be dominant, right? Because this is getting multiplied by a large capacitor. And first of all, the C1 is not a capacitor that you will put explicitly. That's some parasitic capacitance we have. And this is something you are going to add explicitly. And that in turn gets multiplied by again, so that will be dominant in most cases. So you can go ahead and approximate as Cc times. Oops, I'm really sorry. Cc times Gm2 by G2. So now the second pole, in the numerator, which term do you think will be dominant? First term is G2, which is the output conductance. Second term is say a fraction of Gm2. You want what can you say about the ratio of Gm2 by G2? Do you think it will be a large number or a small number? What is Gm2 by G2 in the circuit? It is the gain of the second stage. DC gain of the second stage is Gm2 by G2. That's obviously will be much greater than 1. So then can you comment about Gm2 will be dominant? Okay. So this I can simply, in most cases I can approximate it like this. So it's minus Gm2 times the fraction Cc by C1 plus Cc by C2 plus C1 Cc by C1 plus Cc. Great. Now, of course, the two poles have now split up. Now, besides the two poles, do we have some other thing in the network now? We also have, do we have a 0? We do have a 0, we already computed, right? Does anyone remember the location of 0? Or okay, fine, let's compute, right? Help me compute. So how do I find the 0 now? I'll assume output to be 0. Then I'll apply KCL at one of the nodes. So let's say at the output node I apply, what is the current here? 0. What is the current through C2? That's also 0. What is the current through the capacitor Cc? If I call this voltage as some V1. V1 times V1 of S times SCC. What is the current coming out of Gm2? Plus or minus? Minus Gm2 times V1. Okay. So this must be equal to 0, right? Currents leaving is all 0. So this happens at S equal to Z1. So what is Z1? Gm2 by Cc. And remember, this is a RHP 0. Right? So as we were discussing in the last class, do you think RHP 0 is good for stability or bad for stability? Why? No, okay. Not in terms of root locus, in terms of the delays added. It basically will add more delay. It adds phase lag to the system and it will degrade your phase margin. It's not a great thing to have, right? So I mean, now we have done one nice thing, we have split up the two poles, but in that process we seem to have introduced a right half plane 0. So let's actually see what will happen to the phase margin. So first let me write the transfer function. We have A of S, which is the DC gain A naught, times 1 minus S by Z1, the right half plane 0, and then we have the two LHP poles. Right. So first, what is the DC gain A naught here? I'll show the circuit. What is the DC gain? Yeah, basically the DC gain of the first stage is GM1 by G1 times GM2 by G2. DC gain, I ignore all capacitors, it's just a combination of GM1 G1 and GM2 G2. So it's GM1 by G1, the DC gain of first stage, G2. So now let's me quickly write down the pole locations again. What is the approximate location of the pole, first pole? Okay, I will not write the minus because the way I have written the transfer function is such that I have already taken care of that. Now I don't have to worry about the signs because the 0 is now RHP, the pole is LHP. So what is the pole now? G1 by the Miller capacitance times GM2 by G2 roughly. We'll quickly write down again. The second pole was GM2 CC by C1 plus CC by C2 plus C1 CC by C1 plus CC, and we had an RHP 0 which was at GM2 by CC. So now let us say I want to find the phase margin here. What is the first thing I will need to do? I want to find the phase margin, calculate the phase margin. What is the first information I need? Unity gain frequency is first thing we need to find, right? So omega u. And remember, when we had a first order system of this form, okay, and let's say feedback factor was beta, what was omega u? Beta times A naught times P1, right? Sorry. So if you actually plot the loop gain, so it will basically do this. This was P1 and this was our omega. So this is for a first order system. Now we have a second order system. So in our case, can you make any comments on omega u? Okay, so I mean we have the second order system, but we have added this Miller capacitor and we are trying to make it stable. So how might the if I were to plot the loop gain in the same thing, how will it look like? By adding the capacitor, what were we trying to do with respect to the magnitude plot? What was happening finally? Pole split up. We saw that the system was basically behaving like a first order system around omega u, right? So where do you think the second pole might come now? After omega u. Okay, somewhere after is where we'll have the second pole. So this is where it will come. 0 will come later after that, let's say. But the point I'm making is, if you compensate it properly for a well compensated two-stage OTAs like what we have, the behavior around unity gain frequency is still first order. So what can you say about omega u now then? It approximately is the same because it more or less is a first order system now. So this is basically beta times A naught times P1. Okay, for two stage which is well compensated, I will say. Cool. So let's say now for simplicity I say beta is 1. Can you find out what is omega u? You have all the information here. DC gain is here, first pole is here.
G1 into GM1.
You basically multiplication of these two guys. What is it finally? I mean everything is plus, right? It's frequency. GM1 by CC. Okay. Fine. So let me go to next page. I'll write all the things again. So omega u is what? GM1 by CC. Okay. So let me quickly write the poles. Poles was CC times GM2 by G2. The second pole was roughly at GM2 CC by C1 plus CC. The 0 was at GM2 by CC. Okay, so I'm trying to find the phase margin. So what do I do next? I found the unity gain frequency. What should I do next? I should find the phase at that unity gain frequency. So what is the phase? This is the transfer function. What is the phase contributed by the first pole? At omega u. Huh? Minus 90. Is that okay? I mean, let's say for any random frequency, what is the phase contribution by this guy? Minus tan inverse omega by p1. So now it's omega u by p1. And you see that omega u is actually far apart from p1. So the ratio of omega u by p1 is very large. So for all practical purposes, this is basically minus 90 degrees. Okay. And what is the phase contributed by the second pole? Yeah, but what is it? I don't know what number is this, but what is the expression? Okay, so that's basically minus tan inverse omega u by p2. Oops. And we also have a 0. What is the phase introduced by the 0? That's also minus tan inverse omega u by z1. Okay. So what is the ratio omega u by z1? This is omega u, this is z1, right? Huh? Why is it 0? Okay. No. I mean, I mean that is assuming 0 is much far, but we can't ensure that, right? This is something we can ensure, but second pole we don't know where it comes. No, I mean in terms of the values given, what is the ratio? G1 by G2, right? So I'll simplify it as minus 90. GM1 by GM2. So what is the phase margin now? This is the total phase. So what is the phase margin?
90 minus this. 90.
Yeah, I mean you can say 180 minus magnitude of the phase. So what is that?
90 minus tan inverse of omega u by g2 minus tan inverse of GM1 by g2.
Is that okay? Great. So this is the phase margin. Now you see that the second term here is the phase added by the second pole, and the third term is the phase lag due to the 0, right? Now you want this guy to be large or small?
Small.
You want this to be as small as possible. So this basically gives you one design choice, right? How will you choose GM1 by GM2?
Small.
To be as small as possible. So usually you will find that GM2 is greater than GM1. Okay. And what is the best case phase margin we can get?
90 degree.
That's the best you can get, right? And again, this is the phase margin for a first order system as well. And of course, in practice, you will choose this phase margin based on a lot of conditions. So, for example, say you have a first order system. Again, I'll assume the feedback factor is 1 for now, for simplicity. Oops. So, you have a first order system. Omega u is what? A0 times P1. So what can you say about the closed loop bandwidth? That's also same. That is also equal to omega u. Right? We saw it last class, right? I mean few classes before. The closed loop transfer function is now basically a of s by 1 plus a of s. You work that out, you will find this is a0 by 1 plus a0 by p1. So the bandwidth is approximately this fellow. So if I were to plot the loop gain for this first order, again I will have the same kind of behavior, something like this. So this is my P1, this is omega u. Now if I were to plot the closed loop frequency response, how will it look like? This is the closed loop frequency response. At DC or at very low frequencies, what is the value? Huh? No, what is the value? A0, you know, what is the nominal value of A0? What do you want it to be?
Very large.
It's a very large number. So, what do you think?
1.
It will be close to 1. I mean, it's a unity feedback. I mean, remember, if you have a feedback factor of beta, ideally, what is the closed loop gain?
1 by beta.
It's 1 by beta. Okay, so it's, remember, it's 1 by beta times loop gain by 1 plus loop gain. This factor ideally should be 1, gain is 1 by beta. So this will start here, right, 0 dB. And what is the 3 dB bandwidth?
Omega u.
It is same as omega u. So if I were to draw a Bode approximation, it will do this and follow this, right? I mean, remember, ideally the exact response will look like this. So this will be 3 dB lower. But in Bode approximation, we don't worry about it. We'll just mark it like this. So, okay. Now, see, other way to look at is what is the phase margin for the system? Huh? 90 degree. First order system. I mean, the only pole is here. Omega u is here. They are far apart. Phase is 90 minus 90. So the phase margin is also 90 degrees. Okay, so if the phase margin is 90 degrees, what can you say about the loop gain evaluated at the unity gain frequency?
1.
Magnitude is 1. What about the phase?
90.
Phase margin is 90 degree. So what is the phase?
Minus 1. Minus 90.
Huh?
Minus 90.
Minus 90? Okay, I mean here it's again a first order system. If I were to sketch the phase, it will do this, and around omega u it's close enough to minus 90 degrees. So how can I write the loop gain function? Magnitude is 1, phase is 90, minus 90, e power minus j pi by 2, right, that's all. That's minus j. So if I were to evaluate the closed loop transfer function at the same unity gain frequency, I know it's going to be loop gain by 1 plus loop gain. Beta is 1. So this is Follow? So if I take the magnitude, what is this? 1 by root 2, right? I mean, this is the same thing, 3 dB. I'm essentially looking at the same thing in a different way, that's all. Okay. So now let us say I have a second order system where I have a phase margin of 45 degrees after doing the compensation. So what is the loop gain evaluated at unity gain frequency? Gain is 1 or the magnitude is 1. What is the phase? Minus 135. Okay, phase is always dropping, so e power minus j 3 pi by 4. And again, if you actually find out what is the magnitude of omega u, it will actually be greater than 1. Okay, it's just a complex number, I don't want to do that here. So what will happen is, remember, this is for a phase margin of 90 degrees, right? So if you have a lower phase margin around omega u, you'll have a lot of peaking like this. Okay. I mean, the worst case is, let us say the phase margin is 0 degree. What will happen? Yeah. Phase margin is 180 degree. Loop gain is basically, the phase margin is 180. This will be minus 1. Right? Phase margin is 180. Phase margin is 0 degree means the phase added is minus 180. Minus 1, so loop gain by 1 plus loop gain, it will blow to infinity. So you will basically have, something like this, right? I'll probably quickly write it. So this is for a phase margin of 0. Okay. Again, this kind of peaking is something you don't want in your system finally, right? So it turns out that again, here you see that the expression for the closed loop bandwidth now is not same as omega u, right? Now the bandwidth is somewhere here. Okay. So the expression the fact that closed loop bandwidth is equal to omega u is again valid only if your phase margin is very high. And you can actually find out what should be your minimum phase margin so that there is no peaking in the closed loop response, right? So nominally you want something like this. Okay. I mean, it's not difficult, it's a straightforward calculation. So if you want no peaking in the closed loop response, the maximum peaking occurs around what frequency? Omega u. So you make sure that h of omega u, yeah, this is the maximum you want. You don't want this to be exceeding 1. And it turns out the corresponding phase margin is, does someone remember? 60 degrees. It's a trivial calculation, right? Just put the same thing here and work out. I'll give it as an exercise.
Beta equals to 1.
Beta equal to 1, yeah. It doesn't matter what beta is. So that's why for practical systems you try to keep the phase margin to be greater than 60. That way even the closed loop response doesn't show a lot of peaking. Okay, so there's one other criteria for choosing phase margin. So now we know that for the closed loop system, we want the poles to be lying on, where do you want the poles to be lying on? LHP, yeah. You try to keep it on the real axis, right? Yeah, negative real axis. And from the root locus plot, you remember that the open loop poles were somewhere here, far apart. They did this and branched out like this, right? So now we have this entire real axis to play with, right? I mean, so you can, what do you think might be a reasonable place for you to position the closed loop poles? Where would you want them to lie? I mean, they can basically lie here, or they can lie here, or they can sit on top of each other.
On the top of
Why?
maximum gain.
Why is it maximum gain?
Yeah, we can.
Okay, assume that, gain, for a fixed gain you can actually do this. Okay, assume that the gain is not varying now. For a given DC gain, we have the closed loop poles can be anywhere here, right, on this real axis. Where would you want them to be? That is the open loop poles, right? Open loop poles are still far apart, right? I want the closed loop poles more or less on the real axis. Now my question is, this is also a position on the real axis. I can have them sitting on top of each other also. That is also on real axis. What do you think would be a reasonable choice? Okay, so let's say if they are far apart on the real axis, somewhere here. It's a second order system. What kind of damping is that? Have you guys learnt about damping? No? Over damped. Huh? And what is the damping factor? It's greater than 1. And damping, I mean, you can also, I always prefer to write it in terms of quality factor, which is this is less than half. Okay. So this is where you have the poles to be on the real axis, but they are not on, I mean, they are not equal. Okay. See, again, as I we're discussing, if we have two poles, the time domain response will have something like this, right? Decaying exponential corresponding to each of the poles. And we saw that one of the exponentials will die faster, other will die slower. So your settling response will be dominated by the low frequency pole. Now you want the system to respond very fast, right? So which means you want the dominant pole to be dominant pole in the closed loop system. Do you want it to be at a low frequency or at a high frequency? You want it to be at a high frequency so that the lowest frequency in your closed loop system is high enough that the response decays quickly. So this is your dominant thing, so you try to push it here, but when you do that, this pole also moves closer. So what do you think will be the best place for the closed loop poles now? On the middle, where both of them are on top of each other. So that way both of them are contributing equally, and that's the best case response you can have in time domain. What kind of damping is that? Critically damped, right? And the damping factor is 1 and the quality factor is half. Okay. And do you guys know what is the corresponding phase margin for this? Okay, again I'll give it as an exercise. It's a straightforward calculation. It turns out the phase margin for this is actually 76 degrees roughly. So I mean, if you can hit this phase margin of 76, it's very good. Else you try to keep it greater than 60 degrees at least. And in fact, if the closed loop poles are lying on top of each other, the phase margin was 76 degrees, right? We saw that now. If they are, let us say, if the closed loop poles are somewhere here, or we'll use a different color. What do you think the phase margin might be? It will be higher or smaller? Huh? Closed loop poles are on the S plane. The phase margin will be higher or smaller? Smaller, right? It will have a lot of ringing. Does that make sense? The closed loop poles are on the imaginary axis. I mean, not on the imaginary axis, are lying on the S plane. So you'll have some sigma plus j omega component. So you'll have a lot of ringing. The phase margin is going to be actually very small, right? So here the phase margin is going to be, say, some 4 or 5 degrees, let us say. As you keep coming down, the phase margin will increase and it hits 76 degree at this location. And the moment you branch out like this, eventually it will tend to 90 degrees. See, because when one of the poles moves to infinity, it means that your second pole is far away. You have only one dominant pole. Essentially, it's a first order system that translates to a phase margin of 90 degrees. Okay. Okay, cool. So enough on these things. So let's get back to our two-stage OTA. So this is our two-stage. Oops. So let me draw that quickly again. So this is the first stage. Second stage, the compensation capacitor. So let's say this is G1, C1, and I'll call it GL and CL, including the load capacitors. This is GM1, GM2. Okay. So now tell me, what is the unity gain frequency for this? GM1 by CC. I'll quickly write down the pole locations once again. The pole location was this, GM2 by G2. Second pole was at GM2 CC by C1 plus CC, CL plus C1 CC by C1 plus CC. And the 0 is at GM2 by CC. Okay. And we also saw the phase margin, that was 90 degrees minus tan inverse omega u by P2 minus tan inverse of GM1 by GM2. Okay. So now let us say you are asked to design, and say you are given what can be given, let's say given a phase margin, you are given what is the unity gain frequency you want, and say you are asked to drive a certain load capacitor CL. Okay. So what would you start? I mean, you have to design this now. What would you start with? Omega is given, so these are the given values, right? You are asked to design the OTA so that it has a given omega u, some particular phase margin, and you are told that you are supposed to drive a fixed load capacitor CL. I mean, you have to decide on GM1, GM2, CC, and everything. Huh? From omega u and CL? How will you find it? Omega u is this. Omega u is GM1 by CC, right? I mean, this is clear. This is CC, right? Okay, so I mean, see, this is again a practical design problem, right? I mean, in practice, it's not like you will have 3 unknowns, 3 variables, you have a nice single solution. So in practice, you will have lesser number of constraints and you will have more design variables to play around, right? So here, okay, what do you think? I mean, I've been given phase margin, right? So I also know omega u. I can find P2, but the only unknown is this guy, right? So what can I do? Huh? We know GM2 should be greater than GM1, so what can I do? I mean, we can't ignore. I mean, ignoring means you're assuming GM2 is much greater.
So just GM1 by approximately.
I mean, I can say that, let's say I know that GM2 should be greater than GM1. So I'll say GM2 is, let us say, some 5 times GM1. Right? I'll just assume this. So this way I'll kind of know what this fellow is. So from phase margin and GM2 5 GM1. So from phase margin and the fact that GM2 I have assumed it to be 5 times GM1, what I can get? I can get P2. Fine. And okay, now let's look at expression for P2. P2 is this. So again, so what do you think might be an assumption to make here? To simplify the expression for P2. That's a reasonable assumption, right? See, because CC is an explicit capacitor that I am adding. C1 is a parasitic capacitor which probably will be small, right? So as he is saying, I can assume that CC is much greater than C1. Then this entire thing,
GM2 upon CL plus C1.
no, CL, yeah, again, GM2, first, this fraction is approximately 1, numerator is GM2,
And
denominator I will have, yeah, let me come to that, CL is there, so this approximately C1, it's CL plus C1, what can I approximate CL plus C1 as? CL, because C1 is going to be small, CL is a load capacitor that I want to drive, that's going to be large, okay. So as long as both of them are valid, let me write it, oops. As long as CC is greater than C1 and CL is greater than C1, I can approximate this as GM2 by CL. Okay. So now from P2 what can I find? GM2 I can find. So from P2 I can find what is GM2. That is it. Once GM2 is known, what can I find? GM1 I can find because I assumed GM1 to be 1/5 of GM2. So I know GM1, what can I find next?
CC.
CC I can find, I know omega u, right? So from omega u and GM1, I can find CC. Isn't it? And that kind of completes our design, right? These are the things you want to find. And finally, see, you need to make sure that.
P1.
Huh?
P1.
What is P1? Yeah, I mean, see, finally, these are the design variables we have. Okay. C1 and G1 are all parasitic, intrinsic conductance and capacitance. So finally, after we design the transistor level implementation, we need to ensure that this condition is valid. That C1 is smaller than CC and also C1 is smaller than CL. I mean, we have not looked at the transistor implementation yet, we'll do in the next class, but this is basically how we might want to proceed. Okay. So just last few minutes. So let us say I have now designed for a particular CL and obtained a phase margin. So let us say my CL now increases. What will happen? If CL increases, what will change? P2 will increase or decrease? Decrease. If P2 lowers, what will happen to the phase margin? Decreases. I mean, ideally you want a first order behavior. You want the second pole to be far away from your unity gain frequency. Now by increasing the load cap, I am making it come closer. So the phase margin will increase or reduce? Decrease, right? So I want to retain the same phase margin. So what can I do? I mean, what does phase margin depend on from here?
Omega u by P2.
It depends on the ratio omega u by P2, isn't it? Now P2 has reduced, so this is going to increase. So I need to keep this to be some constant, right? So what are the two things I can do? Huh? No, P2 has reduced. I mean, is that clear? If I increase CL, the second pole P2 has reduced, the phase margin has also reduced. Now to get back the same phase margin, yeah, I need to keep this ratio to be same, right? So what should I do? I can either go and reduce omega u, right? I mean, P2 has now fallen. I want to keep the ratio same as before. So one thing is I can reduce omega u, or I can try to increase P2. Is that fine? Why will decreasing P1 help? I mean, the phase margin depends only on this fellow, right? P1 is not contributing to the phase. P1 has already given 90-degree phase. So changing P1 is not going to help at all. So a second thing is I can try to go and increase P2 again, right? So how will you reduce omega u? CC should decrease or increase. So I can go and increase CC, right? And this also makes sense. I have a larger capacitor, so to compensate it, I need to put a larger capacitor also. Okay. So now let's say I want to take the other route and increase P2. I mean, I want to do that because see, I'm reducing omega u, right? And remember, omega u kind of determines the speed of the op-amp. Approximately that decides the closed loop 3 dB bandwidth. So that is the speed of your op-amp. So you don't want to reduce the speed of the op-amp. I want to keep omega u constant. Okay. So let us say I want to increase P2. So P2 depends on what? GM2 and CL. Now CL has increased. So what can I do to keep the location of P2 same? I can increase GM2. Make sense? Okay. So I mean, okay. So how can I increase GM2? Remember, this is going to be implemented using some transistor. This is a simple common source amplifier, right? So this is connected to some transistor like this. Basically boils down to increasing GM of a transistor. How will you increase the GM of a transistor? No, simple like ways, huh? No, don't. Let's not change the structure. I have something. I want to make simple modifications to increase GM. What will I do? I mean, okay, if I just increase bias current, all the operating point voltages will change, right? I don't want to make any changes. I mean, lot of changes basically. I don't want to change the operating point condition and increase GM. I want to keep VGS minus VTH same and GM must increase. What will you do? If you only increase W by L, again things will change, right? For this, okay, GM is what? W by L. And what is VGS minus VTH?
2ID.
Okay, square root of 2ID by Cox W by L, right? So I want to keep VGS minus VTH constant. I mean, you can see that GM will increase if you increase current or W. But I want to also keep this guy constant. So what should I do?
Increase both ID and W.
I should increase both current and W. Okay. So this way your GM will increase, your operating point voltages will not change. So will be fine. Okay. So one minor thing, see, this is nice, you can do this. Increase ID and W. So now let's say I increase W, right? What do you think can happen? See, I am increasing W again. This node is connected to. This node is connected to the transistor.
C1 will increase, CL will increase.
Yeah, and I am increasing the width of the transistor. So the gate capacitance will increase, and C1 is basically the effective capacitance at that node. That could increase. So you should make sure this assumption is still valid. So we ignored C1 in comparison to CC and CL. So the point I am making is you can't arbitrarily go and increase the sizes of this transistor, because beyond some point it will increase C1 and this assumption need not be valid. Okay. So yeah, sorry, let's stop here.